is focusing on forecasting future energy demand in the smart grid. The smart grid is the next generation power system, innovative because of its connectivity, such as constant communication required in the system, which is provided by the Internet of Things, a system of interrelated devices that may transfer data over a network without requiring human to human or human to computer interaction. But this results in a large volume of data that demands methods more powerful to perform good data analysis and decision making about how much energy to provide over time. The goal of the project is to use representation learning, a research area with the goal of determining suitable features for renewable energy and electrical energy forecasting. Representation learning can determine a representation and use this along with its suitable features to perform the task. These are the papers that are relevant to this project, such as a paper that use covariates within their models, using deep learning methods in a library called Gluonts, and other scalable representation learning methods. The datasets that are used in this project come from Pecan Street Institute datasets, which include 1-minute interval data on circuit level electricity, and more importantly, month-long data from California, New England, New York, and mid-continent regions, where the intervals of the data are either hourly or every 5 minutes data on energy, which is in the form of wind and solar energy or electrical load data. I also wanted to mention that renewable energy exhibits strong volatility and randomness, which leads to the increase of the reserve capacity of electric energy systems and increases the cost of power generation. So the intermittent characteristics of wind and photovoltaic energy bring challenges to safe and stable operations of the power grid, which is another motivation for this project. Some of the early tasks that were performed include feature extraction, data preprocessing, and basic time series analysis. I extracted datetime features, lag features, and window features. I preprocessed the data, removing non-values, and I used autocorrelation functions to determine the properties of the time series data, such as trend. These are features that are used: optimal lag, trend, and the hour. So I was able to form a hierarchical design based on a time-based feature, such as the hour of the day, and a region-based feature, where the hierarchy just disaggregates over smaller and smaller regions that that come with the dataset. So, based on these hierarchical methods, I was able to divide the data frame into separate data frames, forecast the subseries separately, and either merge or concatenate the forecasts at the end. One of the the main ideas that I used in this project is triplet losses with the motivation for linearly separating pairs of sequences, and the original use was for a context word and context random word, since the context of a word should be distant from the context of a random word. And then I can just use this loss function where the base input is compared to a positive input and a negative input. Most of the models involved in this project come from custom GluonTS models. GluonTS is a AWS developed library for probabilistic time series forecasting and modeling, which supports generative and discriminative models. I created my own models by defining the custom training and prediction network and a new estimator that specifies any data processing and uses the networks. Here are examples of how I customized the models. And here are some of the results. Here's the resulting green prediction of the feed-forward model with triplet loss, and as well as other models such as the deep AR estimator and just the simple feed-forward estimator. Thank you.